Do you know that feeling? You're out running, everything's clicking, you feel great, and then ouch, that little twinge, maybe it's knee, maybe the shin, maybe that nagging foot pain. Running's amazing for us mentally and physically, no doubt, but injuries seem to come with the territory for so many people, and you always wonder, why? Why me? Was it the shoes? Okay, let's unpack this. Figuring out why these common running-related musculoskeletal injuries, RRMIs they call them, happen, and how our shoes fit into that picture. Well, it's been tough. Until now, maybe. Today we're doing a deep dive into some really fresh research. It's literally just published. We're looking at a systematic review called A Systematic Review of Finite Element Analysis in Running Footwear Biomechanics, Insights for Running-Related Musculoskeletal Injuries. Quite a title, I know. It's by a big team. Xuanzhen and Xuanzhen, who contributed equally, which is great to see, plus Meizi, Wang, Zixiang, Qitao, Dong, Yaodong, Ming, Zhang, and Wang was the corresponding author. It's in the Journal of Sports Science and Medicine, volume 24, pages 370 to 387, and it just came online June 1st, 2025. So yeah, cutting edge stuff.
It really is. And what makes this so powerful is the method they're reviewing, this finite element analysis, or FE analysis. It's basically an engineering tool. It uses principles from continuum mechanics. Think how materials behave under load, like continuously to solve really complex problems, like how things deform. For running shoes, imagine building a super detailed virtual copy of your foot and the shoe. Then you simulate the forces of running. FE analysis breaks everything down into thousands, sometimes millions, of tiny interconnected digital pieces, elements. And this lets researchers actually quantify what's happening inside the tissues, inside the shoe materials. Stress, strain, things you just can't easily measure on a real person running.
So that's our mission for this deep dive, right? To explore how this FE modeling gives us a window into that foot-shoe interaction. And hopefully see how it can help us finally start reducing those RMIs that plague so many runners. We all know running is massive, it's accessible, great for health. But wow, the injury rates, that's the big downside. It's not trivial. You see figures ranging from maybe 3.2% for experienced cross-country runners, which sounds low, but then up to like 84.9% for novices.
Almost 9 out of 10 beginners getting hurt. It's huge.
That's staggering.
Exactly. And for years, even with shoe tech getting better, we've had this blind spot. We couldn't directly measure the internal mechanics. What's the actual stress inside the bone? How much is the soft tissue deforming? Without that, linking a specific shoe feature or running style directly to injury risk was, well, it was very difficult, mostly guesswork.
We could see things from the outside, but not the internal story.
Precisely.
And that's where FE modeling flips the script. The paper calls it offering more direct and measurable insights. Here's where it gets really interesting, isn't it? It's like getting computational X-ray vision into the foot and shoe during impact, seeing those hidden forces.
Absolutely. And to understand what we're learning, it helps to see how these digital feet, these FE models, are actually put together. It's been quite an evolution. The early models, maybe 15, 20 years ago, were pretty simplified. They often use basic shapes like cylinders or spheres to represent bits of the foot or shoe. You might see the heel bone, the calcaneus, modeled as, say, a cylinder with a hemisphere on top. The heel pad, maybe a thicker cylinder. It was computationally cheap, fast to run the simulations, but obviously lacked anatomical detail, limited accuracy.
Right, a cartoon version almost.
Yeah, kind of, yeah. But now, we've moved towards incredibly realistic and comprehensive models. This is thanks to amazing imaging tech. We use CT scans to get pinpoint accurate bone geometry. MRI scans give us the detail on soft tissues, muscles, ligaments like the plantar fascia, tendons like the Achilles, and then 3D laser scanning can capture the exact external shape of the foot and the shoe.
So you combine all that data.
Exactly. You segment it all out, separate the different tissues and parts digitally, and then reconstruct it into these highly detailed 3D virtual models. And these aren't just simple shapes anymore. We're talking individual bones, cartilage layers, specific ligaments, different muscle groups, the fat pads, plus all the shoe components, the upper mesh, the insole, different midsole layers, the outsole tread, even things like carbon fiber plates or plastic heel counters. Usually things like laces are left out to simplify things a bit.
Okay, so you have this incredibly detailed 3D picture. Then what?
Then comes meshing. You take that complex geometry and break it down digitally into a mesh of small, simple elements. Think like a 3D grid laid over the object. These elements can be tetrahedrons, hexahedrons, little pyramids or cubes, basically.
Building it out of tiny digital blocks.
That's a good way to think about it. Yeah. And there's a trade-off here. More elements mean more accuracy, but also way more computing time. So often researchers use localized mesh refinement. They make the mesh much finer with smaller elements in areas where lots of interesting stuff is happening, like where the foot presses hard into the insole.
Makes sense. Concentrate the detail where it matters.
Precisely. Then, the really crucial step, assigning material properties. Each of those tiny digital elements needs to know how to behave mechanically. Is it stiff, like bone? Squishy like fat, stretchy like a ligament, springy like midsole foam?
How do you figure that out?
It comes from lab testing of actual tissues and materials, or from established values in the scientific literature. Bones might be modeled as linear elastic. They deform proportionally to load, up to a point. Muscles and ligaments, sometimes as 1D truss elements, like tiny ropes with specific stiffness. But for soft tissue and shoe soles, which are more rubbery, you often need more complex, nonlinear hyperelastic models. Things like the Mooney-Rivlin model, which captures that complex squishiness better.
So you're giving each virtual part its own physical rule book.
Exactly. And deciding whether to use properties from literature or try to get personalized data is a big choice. Also, many studies use quasi-static analysis like a snapshot at peak impact because it's faster. But the push is towards fully dynamic simulations that capture the whole landing and push-off phase. Much more complex, but more realistic.
Okay, model built, materials defined. How do you simulate the actual running?
That's the boundary and loading conditions. You need to tell the model what forces are acting on it and how it's constrained. This usually comes from motion capture labs. Data on how the foot hits the ground, the angles, the forces measured by force plates, maybe even estimates of muscle forces. You simulate the ground as a rigid surface, fix parts of the model like the top of the virtual leg bones or maybe the shoe tongue area, and apply the measured or calculated forces. And a really critical part is defining the contact between surfaces, foot and insole, sock and upper, outsole, and ground. How much friction is there? That has a huge effect.
Wow. Okay. And how do you know if the simulation is actually right?
Validation. Absolutely essential. You compare the simulation's outputs like predicted pressure into the foot or ground reaction force curves, or how much the heel pad deforms against real-world experimental measurements. You use statistical tools to see how well they match up. Generally, if the difference, the error, is less than about 10%, the model is considered pretty reliable for drawing conclusions.
That's incredibly thorough. It really paints a picture of the complexity involved. So, okay, we have these sophisticated digital tools. What are they actually telling us? What have we learned about shoes, running form, and injury risk?
Yeah, the applications are where it gets really practical.
Yeah.
Broadly, the studies reviewed fall into two main areas. First is using FE analysis to optimize shoe design features. Think about the midsole, that crucial cushioning layer. Early FE studies confirmed that the shock absorption role of the heel pad and EVA foam showed that having a shoe generally reduced peak pressures compared to barefoot. But it's nuanced. One study showed that as your shoe's midsole wears down, gets thinner, the stress on your actual heel pad increases.
So worn-out shoes literally put more stress on your foot's natural cushioning?
Exactly. And midsole hardness is tricky too. Softer isn't always better. One analysis found that a very soft midsole could actually decrease stability, allowing the heel to roll inwards, more what biomechanists call eversion. But making it harder might reduce stress on the plantar fascia, that band under your foot, but potentially increase the overall load felt elsewhere in the foot. It's a balancing act.
No easy answers then.
Not usually.
Yeah.
And it goes beyond basic midsoles. FE modeling is helping us understand these advanced footwear technologies, AFTs, like carbon fiber plates. They're everywhere now. Simulations suggest thicker plates, loaded in a certain way, can reduce pressure under the sole without increasing stress on the metatarsal bones in the midfoot, which is a concern. And curved plates seem to perform better than flat ones, according to some models.
Interesting. What about minimalist or barefoot style shoes?
Well, one FE study compared barefoot running to using specific barefoot running shoes. Counterintuitively, maybe, the shoes actually showed better pressure distribution and lower peak pressures than pure barefoot. And there are other innovations, like bionic outsoles designed to mimic natural structures. Simulations suggest they can reduce stress on those metatarsals. Even simpler things matter. Studies show well-fitting heel cups and softer insole materials can significantly cut down peak plantar pressure.
So it's helping refine all sorts of design elements. What's the second main area?
The second area is looking at how different running conditions or techniques affect the internal mechanics. For example, one study simulated changing the foot's touchdown velocity. Just slowing down how fast the foot hits the ground resulted in less impact shock and, crucially, an 11.3% decrease in the peak stress within the heel pad tissue itself.
Wow, a direct link between a simple technique change and internal stress reduction.
Right. Another recent study looked at the sole ground contact angle, basically, how flat or angled your foot is when it lands. They found that landing with a slightly flatter foot, decreasing that angle, reduced stress in the bones of the midfoot and forefoot. Yeah. That could potentially lower the risk for metatarsal stress fractures.
These are really powerful insights. It feels like we're moving from just observing runners to actually understanding the internal consequences of different shoes and techniques. It gives designers and runners much more concrete information. So clearly, massive progress. We understand the foot-shoe interaction much better. But the big question, so what does this all mean? Where do we go from here to actually prevent injuries on a larger scale?
That's the million-dollar question, isn't it? The future is really focused on a few key areas. First, continuing to enhance model accuracy and realism, pushing for what the paper calls high biofidelic 3D models. That means seamlessly combining that CT data for Ming's, MRI for soft tissues, 3D scans for surfaces into one ultra-precise digital twin of the foot and shoe.
Even more detail.
Yes, but also making it scalable. Building these super detailed models one by one is time-consuming. So a huge area is personalized shape transformation. The idea is to use clever techniques, maybe statistical models of foot shapes or methods called free-form deformation, to generate a personalized foot model for anyone based on relatively simple measurements, maybe just an external scan of their foot.
So you wouldn't need a CT and MRI for every single runner.
Exactly. That's key for bringing this to, say, custom shoe design for everyone. And AI is playing a role here too, using deep learning to automate tricky steps like identifying bones in scans, creating optimal meshes, maybe even predicting the FE results directly from the inputs, speeding everything up massively.
Okay, better models, personalized models. What else?
Moving towards more dynamic simulations. As I mentioned, capturing the entire running cycle, not just peak impact. And integrating more inputs simultaneously, joint movements, muscle activation patterns, ground forces, all interacting dynamically for a truly holistic simulation. Refining the contact modeling is also vital. How things slide, stick, deform at the interfaces, even considering the effect of socks and different insole materials on friction and pressure.
Right, getting ever closer to reality.
But the absolute biggest hurdle, the major challenge highlighted in the review, is bridging the gap between these calculated stresses and strains in the model and the actual real-world risk of injury. This raises an important question. How do we know when the calculated stress in a virtual bone actually means it's likely to fracture in a real person?
That's the critical link, isn't it?
It is. There's no universal agreement on the bone fracture criteria to use in simulations. Some models look at maximum stress, others look at strain. Others use metrics like the von Mises stress, which combines different stress components. Each approach has pros and cons, but we don't have a definitive threshold that says above this value, injury is likely.
And it probably varies person to person and bone to bone.
Absolutely. That leads to the need for localized bone assessment. We need to figure out the specific failure thresholds for different parts of the foot skeleton. For example, what's the compressive stress that causes the spongy bone in the heel, the trabecular calcaneus, to start yielding or failing? The review mentions some values found in studies, but it varies. We need much more research on these localized thresholds for bones and also for soft tissues like tendons and ligaments under different loading scenarios and with different shoe types. Addressing this is absolutely crucial if we want to move from understanding mechanics to truly predicting and preventing injury.
It sounds like that's the final frontier, translating these amazing simulations into actionable injury risk predictions for individuals. But the potential impact is just enormous. A future where shoes and training aren't just generic, but are specifically tailored based on your unique biomechanics to keep you running healthy.
That's exactly the vision. Imagine going for a fitting, getting a quick scan, and having software simulate your running in different shoe prototypes. It could identify potential high-stress areas based on your specific foot shape and running style, and then guide the design of a shoe, maybe with targeted cushioning here or extra support there, to mitigate those specific risks before they cause an injury.
That would be game-changing.
It really would. A future where running shoes are truly preventative devices, designed not just for performance or general comfort, but actively engineered based on a digital understanding of your individual risk profile. That's where this is all heading.
An incredible prospect. Well, if you found this as fascinating as we have and want to get into the nitty-gritty details, we definitely recommend checking out the full paper. Again, it's a systematic review of finite element analysis in running footwear biomechanics. Insights for running-related musculoskeletal injuries by Yang Song and the team in the Journal of Sports Science and Medicine. It's a deep read, but truly illuminating. And please make sure you follow our channel and turn on those notifications. We'll keep bringing you deep dives into the research that's shaping our understanding of health, performance, and technology.